Well, hi, good morning. Thanks so much for joining me in my shop here today. Hey, I'm going to be going over the schematic for this radio, which turns out to be working even with all of its old parts in there. And I think if I study up on the schematic, I can probably make some better choices about which parts to go after and replace, what order to do them in order to make the next stage, which is replacement of some of these older parts, kind of interesting as I go, and also to reduce the chance of me making a mistake. Wow, that's a challenge. So I don't end up having done work and introduced an error, or worse yet, a couple of errors into this radio, and then spend my time correcting my own mistakes. I'm going to try to avoid that. So the first thing we're going to do is take a look at the schematic and go through it. Okay, so here's the schematic diagram for the radio. What else is on here? Well, quite a bit of information on this page. There's all the parts laid out. I'm just double checking to make sure this is my radio. Yeah. This is a detail of the circuitry that gets engaged when you push the push buttons. Push button oscillator, push button antenna circuit. So that's to help with understanding all this part of the schematic here, where these push buttons are switching in and out these different coils. The set of coils here for the antenna circuitry, and a set of coils here for the local oscillator. So lots going on when you push those buttons. What else we got on? Just generally on the schematic here. Voltage readings on datasheet 69, alignment data on datasheet 64. So see, I think what someone's done is they've cut these different pages apart and pasted it all back together into this one sheet we're looking at now. Detail of dual bass and treble tone control circuit. Dual bass and treble tone control circuit. So I don't know what it's referring to there at all. Datasheet 50. Is there a little inset on here somewhere for that? Tone control, tone control. This would be the tone control right here. Looks pretty darn simple to me. Okay, don't know what that is. Here's some notes here. Push button switch, switch light, moving contact, stationary contact. They all look like they're moving. Maybe the copy didn't do well here. Power switch? Power switch location. Bottom side up, bottom something up. Maybe I can make this a little bigger here. Excuse me. Looks like oscillator section, antenna section. So this is just one of the power switch. So the power switch is one of the push buttons. I don't know what this is about. Yeah, okay, I don't know. Power switch. Maybe this isn't power. This is probably a typical switch. They're showing you how it's typically laid out for all these push button switches here. And they're telling you the antenna section, oscillator. I only assume it says section. So the switch is probably, well, it's got to be switching both these. Sure, it's got to be switching both the antenna coils and the local oscillator coils. So they're just trying to get you straight on how these switches are wired. I think that's all that is. Look at all these little notes here. L3, L6, 7. Maybe that's L5. Variable slugs in all these coils. No doubt that's a big. Hey, how come there's so many coils? This is only a 2-band radio. What's happening here? There's something funny going on. Oh, you know what? These are all for the push buttons. What am I saying? It's a 2-band radio, but has many push buttons to select fixed stations, of course. So these are the coils that are actually associated. Well, it's okay. I don't need to say. Don't say anymore. Stop talking, Jim. Okay, just keep rummaging for now. Here's another big note. This switch is located on frame of switch S2 and is off when push button marked power is depressed. Yeah, that's right. So on this radio, you push in one of those push buttons and the radio turns off. Depressed, and when something or other, switch something or other. So I think it closes when you depress or when you push another push button, of course. Okay, we're almost ready to go through the schematic. Here's some more notes. Well, we'll encounter these notes as we go through also. Uh-oh, what does that say? Yikes. Okay, let's start going through this. Let me shrink it just a bit here. We'll start with the power supply, and then we'll switch up to the antenna and go through the radio. So, power supply transformer. Here we are, one primary, three secondaries, one 5-volter for the rectifier, one high voltage one to produce the B+ to operate all the tubes, and one to heat to supply a power to the heaters of the tubes. Nothing. And the dial light. Dial lamps, 2 lights. Okay, after the rectifier, we have a 10. I'm probably gonna, maybe I'll do the power supply first. So we change out this 10. Then on the other side we got a 16, which I'm pretty sure I saw on the radio. Could change that out. So at this point we've got some useful high voltage DC, maybe 300 volts here. Wait a minute. Yeah, 300 volts here. Let's see where it goes. They said 300 volts. Capacitor here. Is this a big one? Looks like it says 0.25. So that's not really a big one, but it's fair size. Up here to the plate, and over here to the plate through these coils. So this guy's job is to quiet down anything that's here that shouldn't be there. Or in other words, another way of looking at it is to move the effective signal ground onto this line right here. So this line, from a signal point of view, is grounded. Certainly not grounded from a DC point of view, though. That's kind of what this capacitor is doing. That's why it's a fair size one here. And that causes the voltage variations generated from the tube, or resulting in the operation of the tube, to be contained between this coil and the tube itself, like a seesaw, going back and forth. No power wasted, no signal wasted anywhere. I think that's kind of the idea. Force it to seesaw between the tube and the coil here. Anyway, doesn't that leave you all confused? If we carry on here a little further, here's another takeoff with a 10%, what did I say, 14K resistor, I'm not sure. Where is it going? Okay, so some of it's going up here, back to the plate of the detector tube. Okay, and also, oh, here's another big capacitor here, and it's before this resistor. So that's going up to a screen. So this is the screen supply here. This guy's going to quiet it all down after this resistor. And through this one, this is a not so big one, 5600 looks like. Oh my gosh, we're gonna, I'm guessing this gets to the screen of the tube. Oh, that looks like a plate. No, that can't be the plate. The plate is here. Oh, I'm mystified. 6K8. What goes on in a 6K8? Well, I'm not going through this schematic in a very straightforward way, am I? But we're just seeing what's happening to the B+. Now here's, I think, a really interesting situation here. So this would normally be ground, or grounded, or chassied, maybe is a better word. You'd have a lead coming off here to the chassis. But if you notice, there is no lead on this wire going to the chassis anywhere. But there's lots of stuff that does go to the chassis. Look, here's the cathode on the output. Goes straight, output tube goes straight to the chassis, chassis all over the place. There's chassis connections, and I've seen them in the radio. So the power supply's connection to the chassis is actually here. On the other side of this, these two resistors. The result of that is a negative voltage on the chassis. No, let me think about this. That makes the chassis... I gotta think hard about this. Thinking too hard. This is a trick to provide bias, and you know, when I look at diagrams like this and they've drawn the resistor up and over and down, it makes my brain go a little bit cockeyed here. Well, let's see. Well, I'll tell you what I think anyway, without, because hang on a sec, let me just follow this. This is the grid. See, here's the thing, the output tube has no cathode resistor, so how's it getting its grid bias? Oh, so much for what I was saying. Oh yeah, you see, the grid is hooked up. Whoops, the grid. Sorry, I'm jumping all over the place. The grid is hooked up here at this point, and this point is resistor to the chassis, making the chassis a little bit positive to this line, or making this line a little bit negative relative to the chassis because of the voltage division going on here, which I think that's 27. It looks like 27 ohms. This looks like 270 ohms. Frankly, I'm not sure what I'm reading there, but I think that's what's going on there. Okay, now I've really confused the whole thing because I've jumped all over the place, but let's go back. We'll leave the power supply. I've seen enough of that. We'll go back to the antenna now. So the electrons in the antenna are getting sloshed around because of magnetic waves in the atmosphere from transmitters, and that sloshes through these coils. This coil is tuned against this capacitor. This one says broadcast antenna coil. And this one would be short wave antenna coil. It would appear to me that these are not switched in any way. Maybe they are. Maybe something does come down from here. And I am not going to try to sort out these switches. They will cause my head to swell, so I'm not going to do that. So we'll just talk about it on a high level. I know at a high level exactly what these are doing, but specifically wires and all that kind of stuff, I don't know. I'm not going to sweat over it. So somehow through a practice of switching with all these switches, when you're in AM mode, this coil, it becomes the primary of this coil. So this being the secondary, it's driving a signal towards the grid. So I'm going to start at the grid of this tube and work my way back, which I found is easier than trying to come forward through all this stuff. So I come back. So the antenna signal should be here. Small capacitor. Notice it says 10%. That's a hint that this has to be precise. This one here, 5%. It's another hint. These have to be precise capacitors because they're involved in tuning. Down here, down here, down here into the maze of switches, which I've chosen not to study in detail. So, well, look, you can draw a line right up here and not cross any wires all the way up to here. So there's one wire. This is what? Is this a double tube? What is this? Detector oscillator. I'm going to look at this up. I'm going to look this up in the book here because there's too much junk inside this tube here. What is going on? 6K8. I'll have to look that one up. Yeah. It looks like there's just too much in here. Well, you know what? Maybe this is a double tube. One side is operating as the oscillator, developing oscillations, and then the oscillations are fed along with the antenna signal onwards. I think that's what's going on here. It is a two-part tube. Shouldn't be, though. Yeah, I'll have to look in the book. 6K8, this is a little bit of an unusual tube. A little bit. Now, this radio is from the late 30s, right? 1930, 38, 39. So it's got some tubes in it that you won't find in later radios. Okay, so if you switch to a shortwave, then this coil becomes the one that is resonant, I guess maybe through this capacitor or something. And the signal is fed into this coil and then works its way down here, and appropriately selected oscillator coil. Shortwave oscillator, here it is up here. Shortwave, broadcast, and then all these selectable coils for the push buttons. Okay, that was a terrible explanation. But at this tube there are a bunch of signals arriving together. One is what's come from the antenna. Almost the whole shebang is over here. Not quite, it's been tuned a bit. Out of the oscillator comes the oscillator frequency. It's going to be 460 kilohertz higher than your target tuned frequency. It's coming into this tube too. And coming out of this tube is the two signals going in, so all the antenna stuff, the local oscillators coming out, but also the difference between those frequencies and the sum of those frequencies. And since the antenna is not supplying one signal, it's quite a bit coming over here. There's a lot of stuff coming out. Some of the stuff coming out of here, if it happens to be at 460 kilohertz, it's going to find its way through the rest of the radio. Everything else will be rejected at this point. So this is a real busy spot, I think. I really want to examine this point in radios a lot more. Plate of the what they call a detector, which is an earlier way of describing this tube. They never call it a detector anymore. They would call it a mixer or something like that. Okay, so any 460 components of what's coming out of this tube now start traveling through the rest of the radio to this primary of this transformer, into the secondary, onto the grid, gets amplified, onto the primary, onto the secondary, comes over here to the detector now, and the signal is, right now it's swinging above and below zero. You could think of it that way. Through here it's swinging above and below zero. So if you fed that to your speaker, this is not a very good explanation, but let me just go ahead with it. If you fed a signal to this, you know what, I'm not going to go ahead with it. It's not going to work. Take it back. Okay, I just took that stuff back because I was going down a bad road there. Once the signal, the 460 kilohertz signal, gets rectified in this tube, what can be found after that is the audio component that was impressed or suppressed or whatever it is, modulated onto the 460 signal coming through here. So this basically splits the radio signal from the audio signal. You could almost look at it that way if you want. The audio is produced here. Look, top of the volume control. And this capacitor here is going to let the audio part through, but it's going to stop any DC that's sitting here. Some of the DC that's sitting here now, that's resulted from the rectification of the signal coming through here, goes through this fairly large resistor. For some reason I can't fathom, comes over here. It's just a large, you know what I want, I'll say no more. Comes over here. Why? I'm doing my best here. So this should have a negative DC voltage relative to the chassis. It's over here. It's fed up. It goes through this coil, no problem, on the grid. So here we have the AVC voltage being passed out. It's going to come down here and through some machination of wires, it is somehow going to work its way over to here. So basically, the stronger the signal coming through the radio, through the IF, the greater this negative voltage gets developed here at this rectifier, and the greater negative voltage is pushed back onto the grids of these early stages, quieting down or reducing the gain of these tubes. And that's sort of throttles, or it's very much like a governor. Okay, if you know how a governor works on a rotating machine, this is very similar in a way to a governor. So, and for those of you who don't realize this, that's why when you tune an AM radio between stages, the signal disappears, and there's no rectification, there's no DC voltage. These two tubes, their gain shoots up to maximum, and what do you hear? You hear what's there to hear, a big hiss, a big loud hiss. When as you tune in the next signal, DC voltage develops from the rectification, gets on these grids, and as you tune into the station, you'll hear all that noise and hiss disappear. You think the signal is knocking it out or replacing it. That's kind of what's happening, but what's really happening is the volume's being turned down on the radio as you approach this powerful signal automatically. That's what's going on. That's what's really going on. Okay. So we have the radio signal rectified. We've got a little DC to do the governor AVC thing going on back here. Follow forward out of the volume control. All this machination down here is all about tone control, I believe. Linearization of the volume control, so it's not all packed at one end of the volume control, if you follow that. Something like that's going on. So once you get on this side, now it's just straight audio signal right to the grid, amplified, comes out here, high DC here to operate the plate, blocked by this capacitor. Very, very, very important. Oh, I gotta go. Okay, so I ran to my door there because I'm expecting a customer to come and pick up one of his radios today. And when I got out to the door, it was my Jehovah's Witness neighbors coming around to have a chat with me out front of my house about stuff. So I'm back at this now. Now, talking about distractions, that was a fantastic distraction. It goes right here on the volume control. So the audio's coming out of the volume control, getting through this capacitor. Hopefully no DC leaking through with it. Applied to the grid. Follows the plate out. DC blocked here, so the plate voltage doesn't get over here. Signal coming through. Big resistor here, 0.5 meg. Signal goes on the grid. Amplified through this power amplifier tube into the primary of the output transformer that's sitting on the back of the speaker. Secondary hooked up to the voice coil, and we hear it. Ta-da! That's the end of the road. Is there anything really the peculiarity in this radio, or the thing that needs to be known about? Some of the things that you need to know about is how is the biasing done on the output tube? Is there a grid cathode resistor and bypass capacitors? Very, very typical here, but not in this radio. This radio is using this technique, which I failed to explain in any kind of sensible way, but here it is. So just the same, we should be checking for a negative voltage relative to the chassis on this line here. And that will tell us what the bias is. And I can pick it off right up here. I can come right up on the grid. Pick it off. We should check that. This guy gets his bias. As far as I know, this is just a sort of self-biasing on the detector side. Don't quote me on that. And these guys get their bias from the AVC voltage, which may be stabilized by this connection down into here. I don't, you know, and then we could study these, but I'm not going to because it's just too much to study. It's not necessary at this point. Oh, okay, let's read the notes here. I didn't read these notes. Connect cathode ray oscilloscope. Connection to terminal having shielded. So this is typically, it's a really good spot to pick up the output of the radio right onto the top of the volume control. It's generally true in most radios. That's a good spot to go. There's all these adjustments. Everything's on the top or on the apron. Is there nothing from underneath? What about these guys? Oh, here we are. Screw on bottom. So what this tells me is to do the IF alignment, I have to have this radio up in the air, or like it is now, actually. I don't have to worry about that. Not the scale. You know what we should do here while I have the schematic is I should look at these big capacitors and see if they match the sizes in here. Now there's a 10 and a 16, and in the radio I've seen a 10 and a 16. And there's another 10 which is hooked up hooked up to the first tube here. Hooked up to this tube. Is it? It could be that. Can you read that? I can't read that. What's that say? It says I lost track of where I was. That's what it says right here. R12. Wait a minute, is that it? I totally lost track of what I was doing. I had the room effect just hit me here. I zoomed in to looking at the screen, and once I got it zoomed in, the room effect took away my memory. If you don't know what I'm talking about, look up memory room effect on the internet. You'll learn something about yourself. Oh, really? I totally lost what I was doing. Okay, how about some voltage readings, or anywhere where it hints what the voltage should be, anywhere in the circuit here. We see lots of ratings, 400 volt ratings, but I'm looking for an actual notation. Sometimes they put it on the plate of the detector tube because it's usually about 100 volts. It's not full B+. Sometimes they put it on the screens because the screen voltage should be a certain thing, and screens conduct current. Current goes through resistors. Resistors get hot, they wear out, screen voltage goes off. I don't see any voltages written here anywhere. Is there a voltage chart? No, I don't know. There's no voltage chart, not that I have. Voltage table? There's no table. Hey, just come to think of it, where's the alignment instructions? You know, I'm gonna have to read these notes here, but they're pretty long, so I'm not gonna read them on the radio. But just glance through them, and I can see there's a lot of stuff changing when you use these push buttons. So I better read that. Okay. Bottom line, let's do the power supply filter capacitors, the big honkers. So there's these two, obviously. Got to be this one here, and I don't know. We'll have to trace out of the radio and figure out which one of these is showing up. Yeah. Okay, let's switch to the radio here. Okie dokie. Let's get this out of here. So I got clearly 1, 2, 3, and you can see the big plus and minus polarity indicators on here. Other capacitors, you can see like this one that has a black bar. That's not a polarity thing. It's just telling you which of the two leads is attached to the outside foil wrap. So are there any other electrolytic capacitors in here? It's a fairly large one here, but it's not electrolytic. So I think I only see 3. So we'll do these 3. So that's 10, that's 16. These are the 2 either side of the field coil. And then this one, what is this one doing up here anyway? It's one. It's got the original capacitor still connected. I'm going to figure this one out. Let's figure this one out. It goes to the first tube in the radio. Maybe this is just a connection terminal point here. So that is actually pin number 1, 2, 3, 4. Pin number 4 on there. I'm just going to take a peek at the schematic for a moment here myself. Oh, yeah, what am I saying here? Pin number 4. Yeah, can't see pin numbers at all here. 6K8. So we're going to take a look at a 6K8 in my book. 6K8. Triode hexode converter. It is a double tube. It is a double tube. It is full of stuff. So this is just done a little bit differently than many radios. So my guess is, oh, here, let me hold this so you can kind of see it here. See, it's a double tube, 2 cathodes, 2 plates. Pin number 4. Suppressor. And oh, that's interesting. It's got like 2 like suppressor. Oh, what's going on there? It's got 4 grids. Hexode. Well, hex is what, 5? How does that even work? This is a really weird tube. Let me get this on the computer. We can take a better look at it here. Okay, so here's the tube we're dealing with, 6K8. I'm looking on a website called, I thought this was the Valve Museum. Yeah, National Valve Museum, a British website. So it turns out I read this. This is actually a very unusual tube. So I'm going to read all this again out. While you stare at this diagram and wonder what in the heck are they doing. So I'll read this. The 6K8 triode hexode valve was purpose designed as a radio frequency changer. The valve has a common cathode and is unusual within our collection in that the triode and hexode control grids are internally connected. The local oscillator would produce a 7.5 volt peak-to-peak signal from the triode section. The input signal would be coupled to the frequency changer via the top cap connection to grid 3. As a metal enveloped valve or tube, the top cap connection is interesting. The connector is standard, but it is set in an insulating disc that is then sealed into a shaped end of the envelope. This appears quite difficult to manufacture. So here you can study this. I mean, you can look this up on the internet yourself and study this diagram. It made my head explode looking at that. So let's read what it says about it though. The diagram shows the arrangement of the electrodes within the steel shell. This ingenious arrangement avoids the large number of concentric grids used in other mixer designs. The thin metal tube envelope is 25 millimeters in diameter, and excluding the IO, it's just giving you the dimensions of the tube. 6K8 first introduced in 1938, so this was a hot from the tube manufacturers when this radio was being made. So you can think the radio designers where they would have been told, or they would realize that this tube has been designed and is being built, and they would design a radio to use this great tube, which was great for maybe a year, and then it was superseded by other tubes. So so very strange inside here. This is, you know, my imagination looked a lot different than what I see inside here. So they've done some funny things, and far be it from me to get this fully into my head. What I'm going to remember is a 6K8 is a pretty unusual tube. Just remember that. So as for pin 4, so pin 4, grid 2, grid 4. Grid 2, yeah, and it said this grid was connected together, grid 4, connected together internally. So 4, I can't remember why we're looking at this. Okay, let's go back and look at the radio. Okay, I remember what we were doing. We're trying to figure out why there's a great big why there's a big capacitor hooked up to pin 4 of this tube here. Oh my gosh, try and spot which one of these is going to be pin 4 in this diagram. So, oh my gosh. So there's the heater right off of here. This is the cathode. Come on, mouse, don't give out on me now. This is the cathode here. Here's the grids internally connected. Well, see what they're doing? They're showing one plate here and one plate there, and a grid on this side and a grid on that side. And this is like actually be kind of physically how this tube is built. So off of this grid somewhere is a big whopping capacitor. Can't be that. Can it? It goes to ground. Oh, there's something is going wrong here. Let's just follow. Let's follow all these wires here, because there. That's it. That's the capacitor, I bet. See. 39, 350 volts, 10, maybe that's microfarads there, MFD, that says MFD, so it's 10, so that's it. Okay, so that's the other one that I'm looking at. So there, 1, 2, and 3 electrolytic capacitors. Now I don't think there's any others that show up anywhere in here. See, normally I would look for one on the cathode bypass, as a cathode bypass, but there's no resistors, there's no need. So that's it. 3 of those guys. Okay, there we go. Let's go back to the radio here. Okay, so I think what I'm going to try and do here, I'm going to set up to measure the amount of leakage with these 3 capacitors in place, and then going to change them and then measure the leakage again, just using my my shop power supply. So we'll do the current leakage measurement first. The only reason I'm doing it this way is because I'm curious. I just like to know, you know, when I make changes, what's the actual effect of it. So there's a couple ways we can do this now. So we'll do an initial measurement. This is going to cause DC to charge up the positive side of this capacitor, which will charge up everything in the radio, B plus Y's. But because there's no power in the radio, it's not going to operate or anything like that. Let me get my little, because I think we're going to need some precision in this measurement, before and after measurement. I think I'll use my DC meter here, DC clamp-on meter. Set it to DC. Zero it. So this should read the DC current flowing in the power supply. I also have a meter up here, but it's not very accurate. So I'm going to pop this on to standby, let it warm up. read the instructions for that. There they are. Only kidding, of course there's English instructions for the meter too. While we're waiting for that to warm up in my tube collection, I found another great big tube I have. 809. Isn't that a beauty? That's got to be a transmitter tube also. Wow. So I got two big honkin' whopper tubes here. Woo! Don't know if they're good or not. But they're nice to look at. Okay, everything should be ready to go. So we're going to apply a certain pressure, a certain voltage onto this, and we'll see how much current goes through it. Let me zero this again. Good enough. I think that's good enough. Now, anything crazy happen here? Shouldn't. That's my last word. Famous last words. Okay, let's take it up. Up. Up to. So I'm going to set this so the pointer, the voltage pointer up here, is pointing right at 200. That'll be the set point. Current flow is 8 milliamps. The 0 had a 1 on it. Didn't quite 0. Let me write down 8 milliamps. As soon as I find a way to do that. 8 milliamps. It's 11 now. I like 11. 11 sounds nicer. 11 milliamps, which I'm writing down here. 12 now, so maybe this is drifting a little bit. I'm going to cut off the supply voltage. Okay, must be, you can see the voltmeter up here slowly going down, so it's discharging. That's a good sign, actually. Slow discharge. Still 12 going through here? Shouldn't that be going up? Mysteries abound. Maybe this reverse direction I didn't notice. Maybe it was a negative before. That's just hanging on there. Wow, that raises lots of questions. So I'm going to break the circuit here so there can't be any current. Lordy be. Okay. Let's try it again. Hook this up. Zero that out. Flip it on. It's going to be right at 200. 200. This time we're reading 3. Oh my gosh, this test is not going to work well. The amount of current leaking into the radio is so low, it's too low. It's too low to measure accurately. It doesn't even show up on the ammeter up here. So if I change those capacitors, I'm just going to see the same result. Why should I bother changing the capacitors if they're working this well? That's quite a question. I'm going to abandon this attempt here to detect the improvement as I change these capacitors because I believe it's undetectable in any kind of reliable way. What if I try reading the capacity of one of these capacitors? Can I do that with any of these, the way they're hooked up? So this one up here is hooked up with a 500,000 ohm resistor going to somewhere. That's pretty high. Maybe I can read this one. Let's give it a go. You know what? I got a new meter to do this with. Let's try this. Okay, I need to get some experience here. There you have clip leads on it here. So we're going to put the black one on the negative. We'll put the red one on the positive. Now you know what? There could be voltage here already. Voltage fire. Let's check and see. My new cool meter. Okay, so we're reading voltage. Oh my gosh, yeah, 6 volts there. Kind of doing these tests out of order. I should have done this before charging it up. Okay. Yeah, that's supposed to drop to 0. What did I do? I didn't do it right. So I've shorted out the capacitor. We'll leave it shorted for a little while. There's nothing in here. It's reading 32. So this can react to the Earth's magnetic field. Which is why you got to constantly zero this meter. Okay, let's see if we've got nothing left here. I'll remove the short. See, I don't think there's any way we can read that capacitance like that. So not only am I trying to discharge this capacitor, these ones are still in there too. So they're probably all trying to discharge, and these ones might be trying to discharge through a resistor. That means we'll be sitting here for a long time. So let me, now any moment a customer is going to show up here to pick up his radio. I'm going to have to go running. So we know what to do, put shorts on these capacitors and leave them like that for a while. That's a good idea. I'll deal with my customer and come back in and carry on with this afterwards. Okay, just was talking with one of my radio customers, taking back his radio. I'm ready to continue on with this. So these have been discharging for a long time now. In fact, just take a look at this meter because it's got this weird feature on it. How about that, eh? Isn't that kind of odd? Yeah, I think that's odd. Freaking me out. Put that like that. Okay, let's take off these leads that are grounding it. Okay, we do have to look at the meter. Okay, so it's showing a virtual 0 there. So the charge is gone. What was left of it, actually, I think the meter is actually draining that. So we're seeing an effect here I'm going to talk a bit about. So I took the short circuits off the electrolytic capacitors, and as we're sitting here we can see a voltage building up. There's a remote chance that voltage is coming from some other charged capacitor inside the radio. I don't think that's what's happening. Personally, what I think is happening is we're actually seeing a battery effect out of one or many of these capacitors, in which the capacitor is actually generating its own small, very small DC voltage. This is my own personal theory on this. That there's moisture in the capacitor, and that moisture is setting up some literally galvanic action inside the capacitor, and that's where this little voltage is coming from. Which then, if that's true, if the theory is true, then looking for a voltage in an old capacitor would indicate, and finding one would indicate that there's a moisture in it and it's bad. I'm looking for an old capacitor to test. Let me just dig in the garbage can here for a moment. Harder to find than I thought. 2 old capacitors out of the garbage can. Let's put them on here and see if there's a voltage coming out of them. Okay, so first you see a discharge. there was a voltage sitting in here when I first hooked it up. Where's that voltage come from? From my garbage can? I don't think so. And now the voltage is down to about, well, it's probably going to drop a little bit lower. And that's because this meter is drawing charge out of the capacitor. We're talking about tiny amounts of charge here to cause these effects. So this thing has enough strength to drive current into this meter such that it reads 12 millivolts. Not much, eh? But that suggests to me that there's a galvanic thing going on inside here. Let's try this guy. I haven't done enough of this to have any kind of, you know, quantum type view of this. It's all kind of subjective. So this one, it's not doing much at all. And if I were to grab a brand new one, this is the point where I end up with egg on my face, by the way. You shouldn't see anything out here. No initial jump or anything. There was a jump. That's kind of interesting. But quickly, right down to zero. Right down to zero. It's kind of interesting that there was a charge in this. This is just sitting on my bench for weeks and weeks and weeks. Nothing there now. Now that's really curious. I think I got another one laying here that I haven't touched. Yeah. Okay, well, I have touched it. I've touched it like that. That's kind of a dumb move. Let's just try this one. Okay, so what we're watching for is a sudden leap of voltage here. Okay, so point is, moisture turns these things into little batteries. These operate like little batteries. You might have some trouble testing them. I mean, once they're operating like little batteries, they really shouldn't be in your radio. So once again, let's look at what's happened to the voltage here, and then we're going to put it on the capacitor checker. Can't get rid of that. So that's less than 1/10 of a volt. We will now grab some more test leads here. These are large capacitors, so I can use a big long lead from my capacitor checker, which is sitting right over here, a little further over. If I was testing a small capacitor, these leads might have more capacitance than the capacitor. But with these big capacitors, I'll flip the switch here to electrolytic and realize I got the wrong kind of lead here. There we go. I'm going to be putting a voltage on these capacitors, and I need to be sure that it's the right polarity. Black, black, red, red, black to chassis, red to there. So we do some kind of, I wouldn't normally, nothing's normal here. I have two test opportunities here. One is to test for leakage by applying a small DC voltage, not necessarily small, to those capacitors, but in effect I'm applying it to the entire radio. So I can't imagine that this is going to do anything other than close the eye. It suggests that the capacitor is bad. Watching the eye? Huh, how do you like that, eh? $150 volts. Is it going to put 150 volts onto that radio? Wow, I've never done this exact test, which is to just hook up to the power supply filter capacitors and let her rip on here. It's pretty interesting. Very interesting way of testing the whole radio here like this. course, I put a charge on those capacitors. I spent so long getting rid of the charge. Right now there's a short circuit in here while the machine is in this mode. Just letting it sit there for a little bit and bleed out the charge as best we can out of those capacitors. Then I'm gonna measure the capacity of whatever it is I've got this thing hooked up to. In fact, a whole bunch of radio. So again, this is not a normal test I would do. So these are great. These are big. 0.1 microfarads to 50 microfarads. There's a 10, a 16, a 10. This one is 36, so this should be okay. And there's more capacitors along the way on the circuit I'm testing, but they're all quite small compared to these big guys. What do we get? Watch the eye. We get nothing. So something happening. When you get to the outside of the range here, funny things can happen with this instrument. Let's go up here. This is now 20 microfarads to 1,000. This is a more appropriate scale. Okay, so something's not working right there. Something must not be working right. I'm expecting that eye to pop open. It's almost like a... I'm going to pull one lead out of here. It's like it's not hooked up. That's how it's behaving. Could it be my clip lead is a dog? This is the one I was using to power the set. I'll put a short on it. So there's something going on. Apparently your short circuit is about 50 microfarads. Okay, I gotta test the test. This is what happens. Let me grab a electrolytic capacitor. This is 33 microfarads at 400 volts. Negative to the negative, positive to the positive. 33 is what we should be able to measure. 20 to 1,000. So you can't see this, I'm sure, on camera, but although the eye is not opening, there is something going on right in here. I wonder if I can't have this, maybe I need to have this switch here. Not making any difference. Okay, let's go here. This is 0.1 to 50, it's a more appropriate range for a 33. There it goes. Doesn't open all the way. Maybe that doesn't matter in this kind of test. So on the 0.1 to 50 scale, 50, there's 10, and there's 50. It's in the middle. 10, 20, 28. 28 on this meter instead of 33. How much I want to bet it's 33 and the 28 is not accurate. But basically that proves the instrument's working. Let's do a leak test on this brand new transformer here. Brand new capacitor. Electrolytic. 150. Doesn't open all the way. It's a 400 volt capacitor. We can put 250 onto it. That's not very impressive. Now it is electrolytic. All electrolytics have a little bit of a leak in them. So what has all this led me to believe about this radio? It's really suggesting I just leave it all alone. Don't bother changing anything. I mean, every indication is these things are not leaking seriously. Wow. Wow, I gotta think here a little bit. what I could do is I could leave everything as it is. I could do some voltage measurements, verify a few things, B+, grid bias, AVC voltage, see how it's working. I could then align the radio and see how well it performs before doing any part changes. And then from there, go ahead and do part changes. And if I'm doing voltage checks and I find something, then I can hunt down what part might be responsible, like a resistor or something causing an incorrect voltage. That sounds like a more fun approach here with this radio than just getting in and changing all the capacitors at this point. Good. Okay, so I'm going to do a bunch of basic tests on the radio looking for things that are out of sorts. Unfortunately, I don't have a chart with B+ voltages, and some of these radios come with a fantastic chart of resistances from the pins. You can look at the schematic and you can measure like a pin to ground resistance on it too. You can look at the schematic and you can figure out what it should be if you wanted to do that. Do that approach. Yeah, I think that's what I'm going to do. Rather than just go in and start changing capacitors, I'm going to poke around some more with the radio and see if I can detect, I guess, deficiencies. Maybe that's the way to put it. I'll look for deficiencies in the radio. Probably find deficiencies in my knowledge. That's probably what will happen. Well, that's just as good. That's just as good, as far as I'm concerned. Along with fixing and tuning up a radio, I'm fixing and tuning up my own head. Okay, I'm going to leave it there for today, and tomorrow is all about voltages and stuff like that.